Good morning. Welcome everyone to the Grasp on Robotics seminar for today. I'm Pratik Chaudhary. I'm the faculty host for today's talk. As a quick reminder, previous recorded talks are available on the YouTube channel for Grasp. And if you're joined by Zoom, please submit your questions in Zoom, and one of our student hosts will narrate them out for you, or they'll answer at the end of the talk. If you're here in person, just raise your hand and we bring the microphone to you. Just wait for a couple seconds until it comes to you. So to begin with, I would like to introduce Dexter Ong, who is a third-year PhD student in computer science. He works on perception-driven robotics. And Sunning He, who is a senior undergraduate student in computer science. And he works on mapping and semantic scene understanding. Without further ado, let me introduce Antonio Loquercio, one of our very own. Antonio is an assistant professor in electrical and systems engineering. And before he joined Penn, he was a postdoctoral scholar at UC Berkeley. Before that, he did his PhD and master's at the University of Zurich and ETH Zurich. His research interests include learning for robotics, computer vision, and machine learning. And some of the most famous results that you have seen around, whether it is drones racing against human-driven drones, whether it is drones racing in forests, whether it is legged robots navigating the Berkeley campus with vision only. These are all his results. Some of the most exciting work that is happening in robotics today. He has been a part of it. And he has received a number of awards for this. He received the Best ETH Medal for Outstanding Master's Thesis back in 2017. And that was followed by the prestigious Georges Girard PhD Award for his PhD work. And already he has received a number of Best Paper Awards at Coral, TRO, RSS, you name it. Today, he'll tell us about simulation and his perspectives upon it. Please take it away.
Thank you very much, Pratik, for the very kind introduction. Very excited to be here. The talk today is going to be a little bit different than a normal robotics seminar. Since this is in-house, and I'm new, I thought it would be interesting to put a little bit of a higher level perspective to show why I'm so excited about the things that I'm doing. Simulation to real world transfer. If you don't know what this is, don't worry, I'm going to explain throughout the talk. And also show how this inspiration can pave the way to future research direction. Okay, so let us get started. And I want to start not with robots, but with, yeah, okay, it works, but with mammals. Okay, so let's go back to Earth 200 million years ago. The Earth was just out of a massive extinction. 96% of sea animals died. 76% of land animals went extinct. The species who gained the most out of this mass extinction were reptiles. Reptiles, they essentially expanded their niche, multiplied, diversified. They became what are known today as dinosaurs. This was the beginning of the Triassic period. The one who lost control were instead warm-blooded animals. They become smaller and smaller. They were essentially just prey for dinosaurs, became mainly nocturnal, and they were not too different from a mouse today. They are in the direct, we are in the direct connection to them. So like that little brain, that little part over there is our brain 200 million years ago. The interesting thing about mammals was the fact that they had a very small but important trick to their survival repertoire. And this was the ability to simulate the outcome of actions in their head before actually taking them. This was very important of an ability to avoid becoming food for dinosaurs. How did they do it? Well, they introduced a neurological breakthrough. And this is called the neocortex. Just to stress the importance of such a breakthrough, our brain today is made 76% of neocortex. Right? The neocortex looks something like this. This is a 3D representation of the visual part of a mouse neocortex. It has this column-wise structure with very dense connection in a column, but very weak connection between columns. The interesting part of the neocortex is that it essentially processes many of our sensors, but also higher level abilities, like, for example, social reasoning, language, also a motor component. And the interesting fact is that independently of the function that it takes, the neocortex is more or less the same. It looks exactly the same. That's why several neuroscientists propose the idea that an algorithm that it does, it's essentially independent of the function it takes. And this has actually even been shown by experiment. If you disconnect the visual cortex of a mouse and you connect it to the motor cortex, the mouse wouldn't find a difference, right? So there is just one single algorithm, at least that's one hypothesis, that controls these very different functions. So what is this algorithm? There's been a lot of debate, but the main hypothesis right now has been put forward by this paper in the 1919, where essentially it proposes some form of predictive coding or analysis by synthesis. The main idea is that some of the higher level neurons propose an explanation from the low-level neurons, essentially try to predict what was their input, and depending on the error between the prediction and the actual input, they update their hypothesis. And this doesn't happen in a single feed forward and backward pass, but it's actually an hierarchy of such connection. So essentially what it happens, just to decode this a little bit, is a form of we simulate what we think we'll see, and then if we try to ground this simulation to the actual observation. And the fact that our mind works this way has been known for quite a while. Like, people have been tinkering with the visual part of the, this visual understanding for quite a while. This is something that I guess everybody that has taken a vision class has seen before, is this optical illusion where there is a rabbit and a duck. And at any time you can only see one, just because of this fact that our brain works like this. You can only put forward one simulation and explain one observation, but not two at the same time. And this fact that the connection between simulation and recognition is very tight has been known for quite a while. The famous philosopher John Locke actually said that it's very hard to tell apart sensation from judgment, and those two things excite one another. Von Helmholtz put forward a more concrete theory, which was normally called as unconscious inference, where essentially there is this idea of connection between these two senses, and even mathematical geniuses like David Mumford, who got the Field Medal for some time ago, actually got interested in neuroscience and proposed actually an algorithm of how this neurocortex would work. But the big breakthrough, I think, was in 2005 when Carl Friston from UCL actually proposed a practical algorithm that would explain most of the observation in the visual neocortex. This algorithm was something very similar to Bayesian inference and predictive coding. So again, this analysis by synthesis. I'm not going to go into the detail of this, but essentially, this really showed the grounding for this simulation and recognition connection. Just for the sake of science, I want to say that this is just one hypothesis. Some people disagree with this hypothesis. They say that there is not enough not enough grounding in this predictive coding idea, but there is the general understanding in the neuroscience community that simulation and perception are very, very tight. But things get extremely interesting when you consider the fact that there is nothing special about perception. This is about visual perception. The same thing happens for other senses, and in particular for the motor cortex. In this nice paper that I found from Raj Raus, the author of the first paper on the functional interpretation of the neocortex in the 1990s, essentially showed that there is this tight connection between the neocortex and the motor cortex. So like recognition is not only this like decoupled hypothesis synthesis, but this also depends on the actions we take. And this explains also why we can recognize things despite moving our head, moving our eyes, and at the same time explains why we are so good at taking a higher level task, decoupling, like since our brain is hierarchical, decoupling in small subtasks, plan for each of those and execute it. Okay, so I think all in all, this shows more or less the background for my excitement is in this idea of simulation. It seems like it is really at the root of our intelligence, of our perception, of our ability to make decisions. So let me summarize a little bit this like first few slides of prelude to my talk. We have seen that essentially these poor mammalian, they had to like take out a trick to survive becoming prey for dinosaurs. And this was like this idea of simulation. And the way that they do it was like extending the initial recognition, right? So, and they connected those two. We have seen that this is not just, this is only like specific to vision, action, other senses, they all happen under the same algorithm. And sensorimotor simulation is good not only for low-level action, but also for high-level reasoning and planning. Yeah. Yeah.
At which level do you differentiate classic prediction like in like estimation, for example, in Kalman filter?
Yeah.
Because in Kalman filter we have a dynamical model with predictive +1.
Yeah. It was kind of close to my next slide. Yeah, not too far from it. Like the connection between prediction and action has been there, like known to control theorists, and yeah, for a long time, right? Every nice controller has it. I mean, of course, Kalman filter is the more like a predictive part, but you know, like an LQR uses the fact that the system in linear to make prediction about the future and compute in closed form what is going to be the next cost. Model predictive control has a similar idea. You do this for like on a more finite horizon and use the optimization such that you don't have to worry that much about linear system. But you know, all in all, take your favorite controller, take your favorite state estimator. The idea is always the same. There is a tight loop between simulation and action. The problem, though, of all of these things is that they only rely on a very, very simplified model of the world, right? Usually a state-based model. And this is kind of maybe a too restrictive of a modeling assumption of our complex real world. But we're in the 21st century, right? Why doing state-based model when we have so fancy simulators? Yeah. Oh, yes. Yeah. Mm-hmm. Yeah. And in fact, I think like the industry has been pushing for this more and more complex simulation. But what I want to argue in my talk, and this is where I'm going to go in the last part, is that this is the wrong direction. Like we have to work for simulators. We have to find algorithms that work for simulators that are imperfect, because our brain has an imperfect model of the world. I'm going to go there through the end of the talk. Any other question before I continue? Oh, yes, Dinesh. Yeah. Yeah. Well, I mean, of course, like there are other forms of intelligence. What we know, though, is that dinosaurs went extinct, and the only descendant of dinosaurs that actually survived is birds, and birds have a form of simulation in that. So this seems to be like there is an example of convergent evolution. Seems like this is something important. But I mean, of course, right? This is I wouldn't call this a justification of what we do. It's rather a post-hoc explanation such that, we get new ideas. Okay, so we have nice and fancy simulators, and the whole idea of sim to real is to take some of these simulators and train sensorimotor policies in them, either for low-level control or for planning. I hope the video is not choppy. It's maybe a little bit. Okay, but anyway, of course, like the simulator can't model every aspect of the real world. It's much better than a state-based simulator, but for example, it's very hard to model how a human would behave, how a forest looks like. But still, like this kind of technique that I'm very interested in is this idea of sim to real. How you train algorithms only in this simplified version of the real world, and you make them work possibly zero shot in the real world. This idea of sim to real has probably given us one of the most exciting, like the set of most exciting results in robotics in the last few years. Right? We have, in particular, the fact that I'm very excited now is that this has showed a way of taking robots outside of lab-controlled conditions and putting them in the wild. We have seen like legged robots climbing mountains, humanoids walking around. This is kind of from my work. I'm going to speak a little bit more about it later, drone racing. But some people even go as far as say this is a quiet revolution in robotics. I don't know, but definitely something is happening there. And the probably ambitious goal of this talk is trying to make a connection, again, a post-hoc explanation between this way that the mammalian brain works and some of these ideas between sim to real. Why we do this? Well, again, not to justify, but to possibly pave a path towards extending and generalizing such approaches. Okay, so let's start with a little bit of history of sim to real. I guess most of the things like started at least getting exciting in 2017. This paper from Berkeley showed that you don't need an accurate model of the real world. Like you could train a recognition system only from these cartoonish images down there, and then you could use it in the real world. The only thing that you have to do is to like randomize all kind of part of perception, randomize the color, randomize the illumination. And the interesting thing is that at least in this case, the real world seems to be in the distribution of such randomization. This was, I think, at least surprising. People in OpenAI extended on this idea almost immediately. They did the so-called Tactile system, which was able to essentially reconfigure, like do this in-hand reorientation task. It worked more or less around the same ideas of the one before. They had a sensing policy that given some cameras would be able to estimate the object pose, and then a control policy that given the object pose would be able to predict the actions of the robot. Yeah, so kind of this was kind of the predecessor of the more famous work of the Rubik cube, which more or less used the same idea. But all in all, it seems like simulation started to work. We got really excited about this. This was kind of the first year of my PhD. Sorry that the video is choppy. This was the first year of my PhD. We thought, okay, why don't we try this on a little bit more of a dynamic task, right? And this was drone racing. We followed more or less the same recipe, tried to randomize everything, gates, illumination, whatnot. But what we found is that the approach that they proposed, it failed brutally, right? Okay, why is this the case? Well, simply because in drone racing, as you can see in many of these images here, you don't see like your next gate, your next goal every time, right? So like this decoupling between perception and action essentially doesn't work. We had to find something else. What we end up finding, we stumbled on this idea of privileged learning. It was still a prelude to privileged learning, got popularized later by many other works. But the main idea is that you train an expert system with access to privileged information. This for us was a model-based planner controller. Now people train this with RL. And then you use this to supervise an agent that only takes onboard observation and directly predicts the action. Nothing fancy, but it turns out that this idea enabled many more things later. And when we did this, with this change, this coupling together sensing and action, it worked quite well, right? We had these nice results. The drone was nice and slow. It could never seen a real image, never seen this track, was still able to fly through it. I guess many of you might be thinking, okay, how did you get from this to this, right? Many years of work. I guess this is something that we learned. I think we were very lucky in Zurich to not work on papers, but rather on projects, right? And this is something that we have been working on essentially for years. The main ideas behind reaching superhuman, going from that to superhuman performance was essentially better system engineering, fine-tuning, smoothing all the edges. This is the final system that we got. We made one step back towards the OpenAI style, in which we had a perception system and a control system. The main reason is that the track was known in advance. So even if you don't see a gate, since you know the track, you can predict where this is going to be. But the overall idea remained the same, right? I have a perception, I train the control policy only in simulation, and then I deploy it in the real world. The problem, though, and also one of the reasons that it took us so long to get there is a small idea that now it's trivial in insight, but it got us some time, required some time to get it. And so the thing is that if you want to go as fast, get superhuman performance, you need a very, very accurate model of the system. Right? And this is like the model of a quadrotor. The blue part is kind of the usual analytic model, the one that is kind of you compute with forces. There are some extra forces and torque. Those are the ones due to battery, aerodynamics effect. And people usually create an estimator to model them. Now, we spent a lot of time trying to get the best model ever, a globally accurate model that would work more or less everywhere, but it was never enough. The simple idea that got us out of this conundrum was the fact that we don't need a globally accurate model, but just a locally accurate model, something which would be good, extremely accurate, only in the essentially in the neighborhood of the race path. And the way that we did it was essentially take a policy, train it all in like this simplified simulator, evaluate it in the real world, collect the data, essentially compute the difference between what we would predict and what we actually observe, use this to update this local model. It turns out that this difference, so going from a global to a locally accurate model, enabled us to get a model that was good enough with just 30 seconds of data. So kind of quite an interesting change. And yeah, with this model, we obtained the results that, sorry, the video is so choppy. I think some of you guys might have already seen. We have performed the world champions in drone racing. Very high speed were reached during this project, around like 35 miles per hour, all while passing through these like small gates. And the input that we got here was just onboard sensor, like images, like for example this one, and the inertial information. It's interesting to see some of the differences between the human pilots and the autonomous pilot. For example, the autonomous drone was not always faster, but it was much faster at the start, right? It had much lower latency. But something even more interesting was that it was able to take a tighter path in the most difficult maneuvers. right? So this means that it got much better in planning than humans. It could do like long-range planning better than humans could. So I think this shows somewhat, at least gives some evidence of the fact that sensorimotor simulation is definitely useful for low-level skills, like the drone before starting simulation could not fly, but at the same time, you would also get some high-level skills from like this training. So this connection between high-level and low-level gets very fuzzy as soon as we train in systems like this. Okay, but the problem of all these fancy simulators is the fact that they only consider usually one or two of the modalities, vision and perception. But the world is much more complex than that, right? Like, and we know there are many other modalities. Like, for example, if I go in a scene like this, I can predict that this is going to be like something rigid and rough, even before like touching it. And for example, I know quite a lot of information by interacting with the scene that would not be evident by vision alone. Like, for example, over here, like I know that if I touch it, this is going to be like something soft and crumbly. And what we wanted to do, at least one of our hypotheses, is that those kind of simulations are useful to like bring us to the next level of essentially intelligent robots. Okay, so this is kind of what motivated me to study the problem of making a simulator which is multimodal. We did the first step in this direction with some collaborators in Michigan, and we started by adding the sense of touch in like a 3D simulator. But before explaining how this works, I want to give you a little bit of background of how tactile sensing works. Okay, tactile for us is like an asynchronous sensors, but one of the sensors that are most successful right now for robotics are these vision-based touch sensors. I think Dinesh has collaborated in one of the first development of like these sensors. They work in this way. They are essentially cameras with some essentially with some lighting. As soon as like you touch an object, there is some gel in front of the camera, and of course, like the gel would like deform as soon as you touch something. Since there is some lighting on the gel, you would see how the gel changes, and this is strongly correlated to the property of the things that you're touching. I think this is kind of a video that is shown many times. Maybe many of you have seen it before. This is how the gel side sensor works. It essentially transforms information from touch to vision. And this is very nice, right? Because if vision and touch live in the same space, this means that we can actually use classic techniques from 3D rendering and novel view synthesis like NeRF to put both touch and vision in this shared space. And this is essentially what we did, and we called this representation a TARF, like where you could go around in a simulator, not only simulate what you see, but also what it would feel to go there and touch it. But how did we do it? How did we put like this touch and vision in the same space? Well, we built like this very simple apparatus. It's essentially a selfie stick with on top you have a visual camera, and on the bottom you have a digit sensor. These are the frames that you would collect from the digit, and yeah, those are the frames you would see on the camera. And this is how you would use this sensor. Like you first collect a NeRF of the scene, and then like you could go around, touch several places, the wood, the grass, and so on. And the main idea now, we have to put like those two information, vision and touch, in the same space. How did we do it? Well, we can definitely know where the image is taken. Right? This is just the problem of like camera resectioning. We know where this image is with respect to the existing NeRF. But the question is, where is instead our tactile with respect to the NeRF? This is, again, a problem that we can solve using the fact that both of those are cameras. So we can use a calibration procedure to know essentially the transformation between the RGB camera and the tactile camera. the way that we do it is, yes, like using some form of essentially camera calibration. And the idea that we found was the idea of the student. I think is quite elegant. Instead of using like a billboard, what is the equivalent of a calibration board for a tactile sensor? Well, it is essentially this. Yeah, like this is called a Braille board. The Braille board, where essentially that are used by blind people to learn the alphabet. This has some very strong visual and tactile connection. So we could use this to find correspondences and the transformation between one and the other. Classic way of doing it. I guess like all of you that have worked on computer vision are familiar with this equation. I'm not going to go and explain them. But once we were able to do this, and we had this transformation, we can essentially collect the largest data set of visually aligned vision and tactile probes. We did it a little bit everywhere, indoor, outdoor, snow conditions. Since it was like over several months, we collected snow, it was in the summer, really had like the largest data set ever. And we used this data set to train a prediction system that would take as input some images and depth information predicted from a nerve and predict through diffusion how would it feel to touch that part of the nerve, right? It's just kind of a classic generative diffusion model. The way that we did it, yes, is very similar to some other works done in robotics. It's like touching a nerve. It's just, the main idea is that we had like a much better data sets, which enabled us to use a more complex simulators. And that's how the thing in the end would look like. After collecting touch in some part of the scene, then we could essentially navigate new part of the scene and simulate what it would feel like to go there and touch it. Again, since like our model was very general, we used it not only for indoor scenes, but outdoor scenes. This is kind of the backyard of the university one of the backyard of one of the collaborators in the University of Michigan. Like what you'll see essentially, yeah, you can touch anywhere you want. You essentially have this multimodal simulator. We did not yet do a robotics application with it, but we demonstrated from some other visual applications. Some of this was the one that I found most exciting was this material localization, where you could essentially say, what is it that feels like this? And the kind of the network was able to give you some matches in the scene. Like, for example, this is an edge, and it highlights the edge over there. Or, well, I mean, also for some carpet, some microgeometry that would be like very difficult to see without touch. But probably one of the most interesting results was that if we would do discriminative task with this data set that we collected of vision and touch, if we augment the data set with simulated data coming from the nerve, we would get much better performance, right? So this fact that simulation data helps gives some intuition of the fact that, yeah, like simulated information can augment real data. So all in all, this gives us, I think, another connection, even is like very loose, with the way that the mammalian brain works, right? We use the same generative algorithms that we use for images. We can use it for tactile. We can use it for sound. We could use it for whatever sensor we want. And putting them in the same space, of course, helps. Now, for the final part of my talk, the last work I want to present is I want to make another higher level connection between this ability that we have to simulate ourselves with the ability of simulating others, and in particular, learning from others. For those of your interest, this is called social projection theory. It essentially articulates the idea that we essentially predict others as an extended version of ourselves. This is at the basis of a lot of, okay. Since, yeah, my accent is very bad, I know. Yeah, I'm not speaking Italian. If you, If you can't understand, please tell me. Yeah, well, I mean, social projection theory is quite connected to this. Like you put yourself in the shoes of somebody else, and this enables you to essentially predict how people will, what people will do in the future. But I mean, like you can learn from them, right? But at the same time, this enables us to create like tight community, right? You surround yourself with people that are the most similar to you. Anyway, social projection theory, what enabled social projection, which you can find both in humans and in primates, a very important thing that it enabled is the fact that you could see somebody doing something, imagine yourself doing it, and automatically get this skill, right? Turns out this could be something quite useful for robots as well, right? If we could learn just from videos how to do tasks, well, maybe we can simplify a lot of our effort. And this is kind of, we did some first step in this direction. This is kind of what I dedicated this year of the last year of my my postdoc. The main idea is to use videos on YouTube to train a general manipulation policy that could be reused and adapted to any task. Learning from videos is, of course, something, I mean, I don't have to motivate it, right? You could learn a lot from videos. We learn a lot from videos. How much time do we spend on YouTube, like trying to learn things? But in specific to manipulation, for like YouTube data, you could learn something like intuitive physics. Like, for example, if I will take an object and open my hand, the object would fall. Contact poses, how do you actually go and take an object? What are the pre and post contact trajectory? What are human preferences, right? Like I don't usually take a bottle and put it like this. And yeah, what we did is use a lot of videos, use these videos to train a manipulation prior, and then update this manipulation prior for whatever task we want. Okay, this first part is the most interesting. Like the second part is not as interesting, it's just result. So I'm going to spend a little bit of time on how we did it. Essentially, the main idea is to take videos and transform them in essentially a large data set of sensorimotor action for a robot. The way that we did it is through end-object retargeting. And in particular, we casted the problem as a sim-to-real problem to make sure that, well, essentially, this data set would be of high quality and of use in several situations. This is an overview of our approach. We first take some videos. We extract where the human hand is and where the object is in 3D. And then we put those hand object trajectories in a simulator, retarget them to a robot, and like randomize a little bit of everything, the camera, the size, the illuminations, the friction between joints, and use this to collect a very large data set of hand object interactions. So let's first information about the first. How do we go from videos to end object trajectories? We used this, I think, a recent work from Jitendra's group, where they essentially trained this large model that can go from video to end object trajectories. The way that it works is quite interesting. It first proposes a point cloud of the object you are interacting with. Then it uses ChatGPT to recognize which object you have, go on object-verse, find the CAD, and then feed the CAD to that model. It's kind of a complex system, but kind of works. We use this to essentially, yeah, transform this in a robot dataset. The way that we did it is retargeting. Retargeting is a classic problem. I think many of you are familiar. Just want to change human motion into robot motion. But the problem that we had right here is that we wanted to have a version of retargeting that would really work at scale, like it could work for many videos. And we used two key ideas to achieve this and propose a new way of doing it, which we call simulation in the loop retargeting. The first is to use high fidelity dynamics as a constraint of the retargeting process. So not for optimizing, but for constraining it. And having the optimization that proposed the retargeting use a different model than the environment dynamics. Okay, so let me give you a little bit of details of how this actually works. This is the classic equation for retargeting, right? The first component on the left tries to match whatever are the key points of a human hand to the key points of a robot hand, while the second component on the right is just some smoothing of actions. Essentially, we'll make sure that there is not that much energy invested and the control would be similar between time steps. Okay, yeah, I think I've shown this. This is the dynamic function. These are the end key points, and this is kind of the smoothing constraint. The problem of optimizing this function naively, though, is that it is very, very computationally expensive. It can take hours to retarget a single video. Since we wanted to do this at scale, it was absolutely not possible. So what people usually do is not using the real dynamic function, but substitute it for just a kinematic function. You don't consider like essentially friction, all kind of forces, the mass. You just try to match where the hand is to where the robot is, forgetting about like the real physics. This is nice, can work at scale. You can do like, you can transform in a millisecond or in few milliseconds a video to a robot, but this solver is very inaccurate, right? You end up having trajectories that are not realistic. So how can we get the best of both worlds? Well, it turns out that you can make a very small change and get not only speed, but physically realistic trajectory. And this was by changing the second part, the smoothing component. What you do is you create, you change essentially the smoothing part, not of the action between time steps, but you compute it between the difference of the new action that you want to take, computed through the kinematic function, and the actual joint position that the robot is computed through running those actions in a high-fidelity dynamic simulator. So what this means is that now the optimization doesn't have to go through complex dynamics, but the only thing that it does, it makes sure that what you ask, computed from a kinematic simulator, is not too different from what it can be executed, which is computed by running a more complex dynamical system. Yeah.
What's the end effector versus like the joint space?
Oh,
they don't match, right? The degree of freedom of the human hand is much more than the robot.
Yeah, well, it turns out that you can use a very simple trick. The fact that you know, like if you have a robot hand, you can find matches between the robot hand and the human hand in 3D. Like for example, you can say, I want this point to match, this point to match, this point to match, and the palm to match. These are like 3D correspondences on the end effector, and all the rest is optimized through, right? You compute the minimum, those are 3D constraints, and you compute the minimum over IK, which are joint positions. No, the phi is the actual joint position, is proprioception. Right, so you make sure that the action that you ask, AK, the next action, is not too different from the proprioception that you would have, that you achieved by running the simulator. Phi is phi is the state, so the proprioception. A is the action that I want to take in the future, what I would pass to, that leads to phi k at the next iteration. This is, yes, receding horizon, single step. Yes, yeah, if we don't have any other question, I'll continue. It's essentially a trick, right? This is just a trick to make like this retargeting not only accurate, but fast. And of course, what I forgot about the object. What do we do about objects? Well, we took a very simplifying assumption, just forgot about the dynamics of the object, and just like consider their kinematics. Why doing this? Well, we don't know exactly what are the properties of the object. We don't know their friction, their mass, just by looking at videos. So yeah, we just kind of consider the kinematics, and it turns out that this is a fair enough assumption. Also, this fact that we do, like we can essentially have the joint optimization between a simple model and a more complex simulator enable us to do all form of augmentation and have multiple trajectories from a single video. How do we do this? We randomize the object location, we randomize the lighting, we randomize all kinds of things. Okay, so I think this was the main contribution of our work. How do we go from 3D object trajectories to very diverse, physically realistic robot trajectories in a way that is scalable and fast? Now, once we have like this big data set, from there we just kind of turn the crank, like classic approach. We have a transformer to learn a prior using next token prediction from these many sensorimotor trajectories. And we then have this prior fine-tuned either with reinforcement learning or with behavioral cloning on a set of tasks. What we found, and I'm going to go very quick on the results, is essentially that this prior enables us to learn tasks very, very fast, very effectively. Whatever task we were giving it to, essentially this prior enabled a data efficient and robust performance. What was particularly interesting is as for tasks that were not present in the training data set, we got essentially a much better performance than other form of pre-training. Yeah, I think this I mentioned. And another thing that we saw is that not only we got better generalization using this prior, but also much more robustness. Like if we would essentially take the robot and disturbing by applying forces all around, essentially our policy was much more robust than the baselines. And the reason is that through videos, you essentially learned some form of affordances and human preferences. We had over, like, for example, you can see on top hours with respect to learning a policy from scratch. You can learn a much more humanly reasonable way of working with objects. And yeah, this was with reinforcement learning. We did the exact same thing with behavioral cloning. I guess also here we're just turning the crank. The interesting part was that we got much better performance than other things, other way of doing pre-training, visual pre-training in particular. And probably the main interesting fact was that for tasks when we had like very limited amount of demonstration, like something around 5 demonstrations per object, this is kind of where our approach would really shine, right? And this kind of makes sense. With this manipulation prior, we have a general understanding of objects, and it takes only very little demonstration to fine-tune them. And yeah, I think that like these are some videos that are not playing, but like you can believe me, it works for all objects that kind of we were working with. And yeah, so kind of this kind of was, this was kind of, I think, another nice connection, right? This idea of simulation enables us not only to learn by ourselves, but also learn by imitating others. And with this now, I'm gonna go to the really final part, the last few minutes of my presentation, where I'm gonna use one of the things that I think I've not touched yet just enough. It's the fact that recognition and simulation are the two sides of the same coin for the mammalian brain to propose where this is going, right? And what are my interests for the future. What I would really like to do is to take all these ideas of sim to real. I gave you a little bit of history. I've showed you some of the main tricks, domain randomization, adaptation, local models, that make the thing work. But what I think is that those set of tricks that now only few labs are able to reproduce, they're like very hard to actually implement towards a theory, a unifying theory for sim to real that can be used much beyond robotics. The first very important point of this theory is that I believe we should start moving away from these very, very accurate physics-based simulators that are pushed by industry, like by NVIDIA. Like I see a future sim to real happening much more in simulators like TARF. These like tactile-augmented radius fields that don't really have a notion of physics, but they are rather like generative models. And I mean, they would contain all senses beyond vision. And we can only dream of how these simulators will look like, but I think they're gonna be more and more similar to other generative models we are used to, I mean, for example, all kind of vision and language models. They are model of the world. How can we use the information they have for actually acting and decision making? A second point of this unifying theory is, in my opinion, something that we don't yet use enough. It's like this duality between generation and action, right? If there is something that I cannot predict, probably I don't need to, right? Probably I can't act on it. And this connects very, very much to this local model idea that we had in drone racing, right? If, I mean, I can't predict everything in the real world. I can only predict what I actually need for completing my task. And I think this is something people in control theory are very familiar with this topic, right? You can't decrease the uncertainty on the part of the system that you cannot act on, right? How can we use this idea back in sim to real? It's still an open question. And finally, this I think it will require a little bit of a change in mindset. Right now, we are like doing sim to real, specializing a lot for the task and making super fancy, like this give us the ability of doing super fancy videos. But I think we should move away from that. We should definitely condition on the task, but stop this like very specific, this task specialization. This will, I think, enable us to work in a much closer model to how language models and so work. Just conditioning, not specialization. And yeah, I think those are going to be the main topics on which my lab is going to work on. Feel free to get in touch if you're interested. And with this, I'll thank you and looking forward to any questions.
Hi, so I have a question. So first of all, thank you for the talk. It's very amazing talk. So my question is on your unifying theory for sim to real. You said move away from physics-based simulation, includes senses beyond vision. So, but then if this is learning, so I remember a talk from Ilya. He said OpenAI moved away from robotics because they didn't have enough data for robots, right? And so one hypothesis right now is all these data are gonna come from physics-based like simulations. So if you move away, where do you get that data? Is that just gonna be from the videos that we generated? And the other question is, you said don't specialize but condition on the task. But previously in the talk, you said you don't really need a high fidelity model. You just need a very good model for the specific task. So that seems like there's a conflict there. So so that's my two questions.
Okay, so let's go on the first one. Where is the data coming from? I think people underestimate the amount of data that robot can generate by themselves. You know, like if I release a robot and I make it robust enough to operate over days, it will generate much more data than you know I can myself collect. So I guess this is kind of the connection. What we will see in the future is self-supervised, self-generated data. And this will be able, I mean, it is a double advantage. Not only is a lot of data, but it's data that is specific for that robot. right? It will only model the path that it needs. Again, connected to animals, right? Why should I don't know, like a bird model the intricacies of underwater vision? It doesn't need to, right? Okay, so self-generated data is going to be the key. Second, like task. I think it's very connected to my answer before. What we are doing now is a form of specialization in the sense of we have one simulator for flight, one simulator for locomotion, one simulator for manipulation, one set of tricks for locomotion, one set of tricks for manipulation. Like, this is very different from conditioning, right? Where we have the same simulator, maybe the same idea, and we just kind of specialize it on the kind of, we're just conditioning on the task that we have, but we don't change the entire architecture just as we change the task. This is not scalable. Yeah.
Thank you for the interesting talk. I have a question regarding the autonomous racing.
Yeah.
So what is the control architecture that you use?
Like, what do you mean by control architecture? Like, which kind of, can you like specify a little bit more the question?
Like you use MPC, how do you generate trajectories?
Oh no, we don't use MPC. MPC doesn't work when you go very fast.
Yeah, because that was my question. Yeah.
I have like other slides on top. I happy to chat about more about this. Most of my work, but this here I have a funny story. Most of my work during my PhD was on this idea of privileged learning. I use MPC and classical planning to generate very nice trajectories and imitate these from neural networks. Yeah. Go fast, this idea doesn't work at all, right? It breaks as soon as with drones you reach speeds of around 5 to 7 meters per second. The reason why it took us so long to achieve this result is because we wasted 1 year trying to make this work. It doesn't. The way that this works, if you use reinforcement learning to train the policy end-to-end, right? We have essentially, so this is kind of a control algorithm that goes from an estimate of the state coming from, gate detection, Kalman filtering and such, this perception system, takes all this estimate and produces the thrust and body rates of the robot. So this is what works. There are like multiple like papers in our lab that shows why this is the case. I'm happy to chat this more offline if you want.
Okay, great. So I have one more question. Again, on autonomous racing, regarding your algorithm, the drones are trained for a specific environment, or it is generalized?
The drone racing, the fast, the superhuman drone racing is kind of specific to the track. Kind of makes sense, right? Because also human pilots are specific, specialized on the track. The human pilots that we got, we invite them 1 week before to train on the same track. So I guess this is normal.
Great, thank you so much.
Yeah.
Hi, thank you for the talk. It was super interesting. I had one specific question was, I thought your using the neural representation coupled with your understanding of the environment was super interesting. But I saw a semi-recent paper using RGBD information for predicting traversability through scene segmentation, working on robots in real time. And I think using nerfs and stuff like that on robotics is super interesting, a really cool way to go. I was sort of interested in what you think, how you can get that working, if you had ideas for how to get it working on the robot and what benefits it has over existing methods for the future.
I'm not sure, like I understood your question completely. Are you saying like how does NERF for robotics compare to other approaches, or can you specify what other approaches you had in mind?
Absolutely. So there was a semi-recent paper, I'm forgetting where it was from, where you take a legged robot, you put it into a forest, and it segments out the forest and says, "Oh, I see that's a tree.
Yeah.
That's not very traversable. I'm not going to walk into it."
Yeah.
Or stuff like that. So it sort of does this scene understanding online, and then as it walks, it updates what it understands from the scene. From what I understood for your work on coupling this roughness of terrain to a NERF simulation, it was a similar idea for understanding the scene that the robot is in.
Yeah, it's similar, but maybe the main difference is that we are interested in something beyond just vision and geometry. It can contain other senses, which are quite important. In particular, if you are in a forest, maybe sound can help you sometimes as much as vision. So I guess is on a similar line of work. I don't know how far you can push the idea of like making a NERF of the scene you're in and then from there decide. This seems like more a system to kind of thing that you would do a couple of times. But then once you learn that you don't have to crash into a tree, well, why creating a NERF? Right? You can just encode this in a neural network. Yeah. Good, thank you.
Excellent talk. Very nice to see the new results on manipulation as well. I'm wondering, it's the paradigm presented here to go from videos to digital twin pretty much assumes that there is the same embodiment, right?
Yeah.
Is there any way to have like a body distillation, something that works like to the closest body, but not exactly the same?
Yeah, that's
one. And
yeah,
the second
good
is
question.
that was heavily kinematics, but you have a lot of other work on locomotion, which has dynamics, right?
Yeah.
Can you tell us a little more about the challenges there as well?
Yeah. Okay, so like let's start with the first question being what if like your robot is different from the human? I guess the main assumption here is not that they are exactly the same, but rather they can act in essentially a similar way. Maybe what we could do is to change the optimization from matching the key points on a hand to matching the results of actions, right? I want this bottle to be lifted by 30 centimeters. I don't care how you robot you do it. I don't care how the human does it. The optimization is through objects. It's object-centric and not anymore human-centric. So that's how I would do it. It's another question whether we want to have robots that are very different from humans. I guess here we can argue, right? I would like robots that are similar to humans such that, we can, just because the world is made for humans, so their integration would be easier. But I think there are counter arguments to this. I'm not going to go into that part, or we can go into this offline. Second question, dynamics. Yeah, dynamics kind of is very nice with legged robots and with drones, just because you have very few interaction with the environment. I mean, with drones, the less interaction you have, the better it is, right? Means you're not crashing. With legged robots, you have only interaction through feet. And it turns out you don't have to model this as well. Kind of nice, right? You don't have to model sand, complicated grass. You just kind of tinker a little bit with friction, have like these weird complex terrains. Here we go. Like you have a nice working policy. I don't think this is gonna work for more complex like manipulation problem, just because the number of interaction with the environment is much harder. And that's why we have to find approaches to cope against the fact that dynamics is just not feasible to simulate in real time.
Yeah, so I have another follow-up question to my previous question on simulation.
Yeah.
So you said we should move away from physics-based simulation, but so like, do you mean that it's only for data generation, or it's the actual action or the control of the robots? So for example, in the retargeting example, you did have a kinematics model in there, right?
Yeah.
So you mean like maybe for the robot, it should still have some sort of physics-based model in it for the action taking, and then you self-generate data, and then so is that what you meant?
I think, okay, on the short term, yes, right? On the long term, I have this belief that I cannot support. It's just an hypothesis that we can learn both, like without any physics, right? Just through interactions. But yeah, this is an hypothesis, right? We can disagree or agree.
Right. And also, so like Google, they did do this like large robot army farm for data collection.
Yeah.
Right. So I would say that's the kind of self-generated data that you were describing. But eventually that also didn't work. Do you think there's anything that
The problem of that was like constrained environments, right? They were working on these like few objects in front of them, and I think you need to go in the real world to get useful data.
So just to give an example, right? If I have an empty ketchup bottle and one that's full, although they both have the same shape, how I manipulate both of them will be different, because so just learning based on the kinematics alone would be insufficient. That's in my opinion. So, and it might work in certain cases as long as I can have a robot that overcomes those assumptions I make. But in the end, if you're thinking of generalizing that, I feel like it's going to be an issue. How does that really?
Yeah. Okay, so like, think of it like this. If you have an empty bottle or a water bottle, but your task is lifting this bottle, in both cases, your approach is going to be the same. You need to get close, you have to put your hand around it, and you have to put it up. Okay, so this is constant. This is independent of what is it inside. To some extent, right? If it is stuck, then you can't do anything with it. The rest, though, how much force you apply, how much strength you have, like on your fingers, that can be learned through interaction. Right? You can essentially try. You can imagine trying it a couple of times. First, you see, okay, I've done this. Didn't work very well, is slipping. So like I can try it again, apply more force, here we go, now it is up. And this is the way that even as humans work, right? We don't know for sure what is in front of us. We just make hypotheses. We try and test if this hypothesis is true. If it is true, good. If it is not true, we change the hypothesis, change the way we act, and here we go. I think the same paradigm is going to work also for robots. It's going to make it robust to this fact that we don't have really a physics simulator for learning these high-level skills.
Hi, I have a more big picture question. I found your presentation on your nerve plus other senses to be interesting, and then you followed that up with demonstrated interactions from humans.
Yeah.
Do you view those as two separate kind of things, or do you plan to incorporate them? It seems like one of the big drawbacks of having to learn a nerve for a static scene is you can't interact with that scene in any meaningful way.
Yeah.
Yeah.
I think they all go under the umbrella of learning from videos. I mean, what is nerve, right? Is a video of a scene, and you are making a good point. Like human can be put in the same shared 3D space, moving and interacting. I guess this is like a very active line of research, how to have this novel view synthesis work with dynamic objects. There has been a lot of advances in this direction, which I think we will leverage. So like, all in all, I agree with your observation. What I want to say, though, is that it might be that in the future, we won't need a nerve at all. right? A nerf might be an over kind of complication for the thing that we want to do. I don't have a very accurate 3D reconstruction of the world, but I still know like what I should do next.
Hello, amazing talk. I have a question. So I think it makes sense to make a robot learn this by itself. But I think the main problem of the robot learning is the training efficiency. For example, if you have a better physics simulator, do you think this would make the robot learning easier or make more efficient rather than you like just let it learn from scratch?
Yeah. I mean, of course, like if we have a nice and accurate physics simulator, we should use it. And those like all results that we see right now in Sim2Real use a very accurate physics simulator, yes. My point is that this is not a scalable way of moving forward. We can get some nice results on some of these like tasks, but we are not going to be able to have general robots going through this. And my intuition here is that we will have to like sacrifice, give up this idea of efficiency. Okay, we are not going to have our robot policy ready in like one night. No problem. We also don't have kids that are ready to, you know, like drive a Formula 1 car in one day. That's also no problem. It might take more time for the robots to like learn, to interact with their environment and to act. Of course, this opens a new research question: how we do this safely? Don't we destroy the robot and the environment for doing it? But that's kind of very valid, interesting question. I think that is much more scalable. We let robots interact with the real world, learn from this interaction, and not like in a straight way as doing self-supervised learning, but rather by building simulators of what they see. That's kind of my philosophy. Yeah. Yeah.
The way that you solve it is that it's not the case that you're born tabula rasa with landscape.
Yeah.
Evolutionary timescale of information.
Yes.
What is the right thing to? What are the right things to try out in human? There's not learning that happens.
Yeah.
More so in humans than any other argument.
Yeah.
Like a deer can walk on its legs. You know, you've heard people talk about it.
Yeah.
A deer can walk on its legs in 5 months after it's born, and so there is, you know, learning that it comes with. With a robot, like instantiating that learning tabula rasa on a new robot versus whether we should try to mimic the evolutionary timescales of learning. That might happen for biology, but do it inside a simulator.
Yeah. But why should we, like my answer for this is, why should we do tabula rasa? Why can't we use internet scale data as a pre-training? Right? It might not have the maybe low-level sensorimotor information. That's for sure. How much of that we need, it's maybe unclear, right? It's feasible to think that if in the future we have a very nice video model, like that video model needs to have some basics of physics to actually be generalizable. So fine-tuning those features on a very limited amount of robot data might already give you all this physics and basics information that you need. So yeah, I'm not arguing for completely self-supervised learning. That would be an Alyosha Efros view that I'm not taking. I'm just arguing for moving away from very high quality simulators. That is not scalable.
Hi, Professor. Thank you for an impressive talk. And I understand that learning from human videos could provide a great potential to do generalization. But I mean, retargeting the human videos to the simulation, I wonder if this could lose some like diverse information of the human videos, like the diverse environments.
Yeah, like you definitely, like this through retargeting, you would lose diversity, but you can get it back using the fact that this retargeting happens in a high quality, high fidelity simulator. So you put back in more or less everything that you lose. You can put different kind of sensors, different kind of, like friction and dynamics. So like this simulation in the loop retargeting tries to make up for like whatever you lose by going through this like constrained 3D representation. Yeah.
Thank you for all the questions. A very robust questioning. Let's thank the speaker again. And as some closing remarks, next Friday, we will have Zach Casas from the Ohio State University for the Grasping Robotics seminar. Thank you so much.